In previous videos, we saw how a definite integral was defined as the limit of a Riemann sum, and we saw how to visualize it as an area under a curve or sometimes minus the area over a curve. So in this video, we're going to talk about some of the main properties of integrals. And the first one is what happens when you try to integrate a constant. The integral of constant from a to b, I claim, is just that constant times b minus a. And this works for all constants a, b, and c. Now this is pretty easy to visualize in terms of areas because if this height is c, then what's the area under the curve y equals c from a to b? Well, that's just a rectangle. Its width is b minus a, its height is c, so you get c times b minus a. But you have to be a little bit careful because when drawing pictures, because you have to ask yourself, well, what if c is negative? What if b is negative, if b is less than a? There are different cases, and drawing one picture is suggestive. It's good for your intuition, but you got to be careful. So let's go back to the definition. If we do a Riemann sum, we take the sum of f of xi. Well, no matter what xi is, f of x is a constant, times delta x. We add them all up. Well, all of the delta x's are b minus a over n. We've got n of those terms, so we got cb minus a over n times n. That's just c times b minus a. And this works no matter whether c is positive or negative, whether b is bigger than a or less than a, it always works. Great, one property down, 5 to go. Second property is that what you get by integrating the sum of two functions is what you get by integrating one of those functions plus what you get by integrating the other one. And this again, we go to our sums. If we do the Riemann sum plus f plus g, you have to plug in f plus g at the function xi star. So that's f of xi star plus g of xi star times delta x and add them all up. And of course, you can just split that up as f of xi star delta x plus g of xi star delta x. Okay, and when you do that, when you take a limit, this expression becomes the integral of f plus g dx. This becomes the integral of f dx. This becomes the integral of g dx. So the integral of the sum is the integral of the first function plus the integral of the second function. And we could have done the exact same argument for a difference. Instead of talking about f plus g, we talked about f minus g. We would have just had the exact same argument and the exact same result, only with minus signs instead of plus signs. The next thing is a multiple of a function. If you know how to integrate x squared, do you know how to integrate 3x squared? Well, sure, you just pull the constant out. The integral of a constant times f is a constant times the integral of f. Again, that's because the sum of a constant times f is the constant times the sum of f. Basic properties about sums turn into the analogous properties about integrals because integrals are just limits of sums. Okay. Next thing is what happens if you try to integrate, instead of from 2 to 5, what happens if you try to integrate from 5 to 2? And I claim that makes sense. There's nothing in the definition that says that you have to have a starting point that's to the left of your endpoint. You can integrate from b to a. It makes sense, and it gives you minus what you'd have if you integrated from a to b. Let's see why. If you integrate from a to b, what you have to do is you have to break things up into a certain number of intervals, in this case 5, and then you would define your points. You would call this x0, this x1, this x2, this x3, this x4, and this x5. And then you would say that delta x is b minus a over 5. And then you might pick a point from the first interval, a point from the second interval, a point from the third interval, a point from the fourth interval, a point from the fifth interval, and add up the function values at those points. Now, if you did it from B to A instead, let's pick a different, what color should I use? If you go from B to A, then this is your x0, and this is your x1, and this is your x2, and this is your x3, and this is your x4, and this is your x5, and delta x is A minus B over 5. And then you have to pick points within each interval, and we could pick the exact same points. Now, the order of the intervals is different. Instead of saying first this, then this, then this, then this, then this, we're going first this, then this, then this, then this, then this. But when we write the sum as I goes from 1 to n, okay, we're doing the same points but in a different order. F of xi star, we get the same points, but now delta x is negative because delta x is the end point minus the beginning point. It's not b minus a over n, it's a minus b over n. So we wind up with the same sum except with a minus sign. Take the limit, you get the same integral except with a minus sign. So it is perfectly okay to integrate from 5 to 2. Integrating from 5 to 2 is minus integrating from 2 to 5. Okay. What happens when you integrate from a to a? Well, I claim when you integrate from a to a of any function, you get 0. And from an area point of view, that's pretty clear. What's the area under the curve between a and a? I don't care how high it is, it's got 0 width, it has no area. Or if you do it from the definition, delta x is a minus a over n, well that's 0. And all of your xi's are a, and your xi stars are a, and your Riemann sum is f of a times 0, added up a whole bunch of times. Well, 0 added up, 0 plus 0 plus 0 plus 0 plus 0 is still 0. And then the last property is that if you integrate from a to c, that's the same as integrating from a to b plus what you get from integrating from b to c. And most of the time, there's a simple picture from that. The integral from a to c is all of this area. The integral from a to b is the green area. The integral from b to c is the orange area. If you take the total area, well, it's the sum of the green area plus the orange area. Total area equals green area plus orange area. Pretty simple. But you have to be careful because nobody says that B had to be somewhere between A and C. This rule works even if B is bigger than C, or if B is less than A. For example, there are a bunch of different orders. We'll go through one of them and I'll leave the rest to you. If you went from A to, if A to C and then B is bigger than C, well then, from the same argument we had before, the integral from A to B is the integral from A to C plus the integral from C to B. But the integral from C to B is minus the integral from B to C. So now you put this on the other side of the equation and you get the integral from A to B plus the integral from B to C is the integral from A to C. So this rule works even if the points are in a funny order. So to sum up, our 6 rules. The integral of a constant is that constant times b minus a. The integral of the sum of two functions is the integral of the first function plus the integral of the second function. The integral of the difference of two functions is the integral of the first function minus the integral of the second function. If you multiply by a function by a constant, you can pull it out. Integral from b to a is minus the integral from a to b. Integral from a to a is 0. And the integral from a to c is the integral from a to b plus the integral from b to c.